Unequal N. Whether by design, accident, or necessity, the number of subjects in each of the various conditions in an experiment may not be equal. For example, the sample sizes for the obesity and relationships case study are shown here. Although the sample sizes were approximately equal, there were more subjects in the acquaintance typical condition than any other. Since N is used to refer to the sample size of an individual group, designs with unequal sample sizes are sometimes referred to as designs with unequal N. Here we consider an absurd design to illustrate the main problem caused by unequal N. Suppose an experimenter were interested in the effect of diet and exercise on cholesterol. The sample sizes are shown in the table. What makes this example absurd is that there are no subjects in either the low-fat, no exercise condition or the high-fat, moderate exercise condition. The hypothetical data showing change in cholesterol are shown here. The last column shows the mean change in cholesterol for the two diet conditions, whereas the last row shows the mean change for the two exercise conditions. The value of -15 in the lower rightmost cell in the table is the mean of all subjects. We see from the last column that those on the low-fat diet lowered their cholesterol an average of 25 units, whereas those on the high-fat diet lowered theirs by only 5 units. However, there is no way of knowing whether the difference is due to diet or to exercise, since every subject in the low-fat condition was in the moderate exercise condition and every subject in the high-fat condition was in the no exercise condition. Therefore, diet and exercise are completely confounded. The problem with unequal N is that it causes confounding. Understanding the difference between weighted and unweighted is critical for understanding how to deal with the confounding results from unequal N. We will explain this difference using the data shown here. In this experiment, diet and exercise are confounded because 4 out of 5 subjects in the low-fat condition exercised, as compared to 1 out of 5 in the high-fat condition. The weighted mean for low-fat is computed as the mean of the low-fat moderate exercise condition and the low-fat no exercise mean, weighted in accordance with sample size. To compute a weighted mean, you multiply each mean by its sample size and divide by n, the total number of observations. Since there are 4 subjects in the low-fat moderate exercise condition and 1 subject in the low-fat no exercise condition, the means are weighted by factors of 4 and 1. Therefore, the weighted mean for low-fat is 4 times -27.5 plus 1 times -20 is all divided by 5. This equals -26. The weighted mean for the low-fat condition is also the mean of all 5 scores in this condition. Thus, if you ignore the factor exercise, you are implicitly computing weighted means. The unweighted mean for the low-fat condition is simply the mean of the two means of -27.5 and -20. The mean of these numbers is -23.75. One way to evaluate the main effect of diet is to compare the weighted mean for the low-fat diet, which is -26, with the weighted mean for the high-fat diet, which is -4. This difference of -22 is called the effect of diet ignoring exercise, and is misleading since most of the low-fat subjects exercised and the most of the high-fat subjects did not. However, the difference between the unweighted mean of negative 23.75 and negative 8.25, which equals negative 15.5, is not affected by this confounding and is therefore a better measure of the main effect. In short, the weighted means ignore the effects of other variables, exercised in this sample, and resulting in confounding. Weighted means control for the effect of other variables and therefore eliminate the confounding. Statistical analysis programs use different terms for means that are computed controlling for other effects. SPSS calls them eliminated marginal means, whereas SAS and SASJMP called them least squares means. No method for dealing with unequal sample sizes is valid if the experimental treatment is the source of the unequal sample sizes. Imagine an experiment seeking to determine whether publicly performing an embarrassing act would affect one's attitude about public speaking. In this imaginary experiment, the experimental group is asked to reveal to a group of people the most embarrassing thing they have ever done. The control group is asked to describe what they had for their last meal. 20 subjects are recruited for the experiment and randomly divided into 2 equal groups of 10, one for the experimental treatment and one for the control. Following the description, subjects are given an attitude survey concerning public speaking. This seems like a valid experimental design. However, of the 10 subjects in the experimental group, 4 withdrew from the experiment because they did not wish to publicly describe an embarrassing situation. None of the subjects in the control group withdrew. Even if the data analysis shows a significant effect, it would not be valid to conclude that the treatment had an effect because a likely alternative explanation cannot be ruled out. Namely, subjects who were willing to describe an embarrassing situation differed from those who were not even before the experiment began in their attitude toward public speaking. Thus, the differential dropout rate destroyed the random assignment of subjects to conditions, a critical feature of the experimental design. No amount of statistical adjustment can compensate for this flaw.